So I am opening my camera. Hi, I am Christina Stratigaki from UBTech GR. This webinar is organized within the context of an EU-funded project named Rainbow, which tries to design an open, trusted fog computing platform that will facilitate the deployment, orchestration, management of scalable and heterogeneous, and secure IoT services and cross-cloud apps. So within the context of this project, one of our three key demonstrators is MSP, where they have a use case focused on the power line surveillance via swarm of drones. So this webinar today is dedicated to describe their use case, their problem and challenges that they had, and what is the proposed solution on their scenario within and with the help of the Rainbow platform. How the architecture was designed and drafted, and what are the key benefits of using Rainbow in their scenarios and in their deployments. And we will wrap up the meeting with some results and conclusions on their scenarios and how Rainbow performed within this use case scenario. So without further ado, after introducing the project and the scope of this webinar, I would like also to introduce you to the CEO of MSP, which is Winiek, and he will perform the presentation, and he will cover the points that we see here in this agenda. So, Winiek, I believe that you can start unless you want to say some introductory words in advance. Thanks.
Thank you, Christina. Hello to everybody. Welcome to the use case 3 presentation within the project, which was mentioned by Christina. We are the MSP company from Poland. I will skip the agenda once more, and let me before the presentation of the demo, present briefly our company. We exist on the market since 2001, so we have over 20 years of experience in unmanned aerial systems branch. It is quite a difficult market, but we successfully keep on existing, let's say. We are an innovative company, and we took part in numerous R&D and commercial projects for dealing with different aspects of unmanned systems. During our existence, we realized dozens of unmanned aerial platforms and systems, weighing from half kilo up to 150 kilo. And we have completed a lot of projects, commercial projects for different customers from different branches, aerospace, energy, and defense industry. During this time, we have collected a lot of knowledge and experience, outstanding experience in the design and manufacture of aircraft structures, autonomous control systems, stabilized sensor suspensions, integration of different sensors, platforms, and also test in flight performance. We can say that we cover almost 100% of UAV technology, except radio links. In the current project, in the Rainbow project, we are responsible for the drone use case design, test, and validation. So let's start with the use case description and starting with the problem statement. So today, Many people that can say that drones can do this, can do that, not thinking about limitations. But especially concerning large area projects, there are a lot of limitations, and aware operators are conscious about them. Examples of such operations are either large area projects, like here on the left. This is photogrammetric project, where we need to collect a set of data for areas of dozens or even hundreds of square kilometers. And on the right, there is an example of linear object, which can be power line infrastructure, railroad, roads, water lines, pipelines, and so on. So these examples of projects require multiple flight missions, and there are some issues and challenges concerning with this. So what are the issues today? Because for tomorrow we want to make the system completely automatic, but today we have to face with different issues. The basic one is that we use single drones, which can fly only within the other radio link, range, or visual line of sight. So if drone starts from the point, flies along the route, and in the moment or before the moment that the radio link can decrease, it finishes the route and flies back to the operator and lands here. So we cannot use the full capability of the flying drone. The second issue is issue of coordination of operations of a group of drones. Currently, if we use a group of drones covering the large area of operation, the coordination of flights, this is the coordination between operators. They agree between themselves where to fly, which part of the mission to cover. They have to take care of everything to prepare the flight, to supervise the flight, to finish the flight with all the activities. And this takes time, consumes the possibility to coordinate the work of single drones for large areas. Then the optimal use of batteries of individual drones. Currently, operators save some reserve of the energy for the cases of emergency situations, for the flight which is not productive flight, for example, to fly to the waypoint or to return to the landing point. So the part of the energy is used for a not productive flight phase. If we save some energy from all of the single drones, then we can get a good profit on the scale of a large project. Another issue are overlaps designed with a quite large margin of safety. These overlaps are necessary because they assure the continuity of data required. So if we minimize these overlaps, and this can be done through the automation of route plannings, we'll save a lot of flying for the productive phase of the mission. Then another issue concerns the control of data, which is usually performed randomly after the drone lands. So we quickly check whether some photos are correct or not, or we perform the full control of all the data in the office. So after the flying part of the project is finished, and then quite often it appears that there are many data incorrect, images that are incorrect, and there is a necessity to go to the field, run flying procedures again, and it again consumes the time and resources. Again, another issue is that currently carried out missions require significant operator participation. This is due to the fact, of course, that one operator controls one drone. So the single operator is responsible for everything what is necessary for the flight, for the mission, for route preparation, preparation of the drone for the flight, supervising the drone, and so on and so on. So if you fly 10 drones, then 10 operators are necessary. So we expect that introducing automation of planning procedures, distribution of flight plans would give us a lot of reserve for the mission operation. Two more issues, probably not all, but these are the examples. Occurrence of flight disruptions during the flight, mainly due to fail-safe procedure, which occurred due to temporary link losses. It happens from time to time in different situations, and then the fail-safe procedure either allow to continue the mission after some time, or can finish the flight of the drone and force him to return to the landing point. So then the part of the mission is simply lost. And the last issue, probably influencing in the most level to the efficiency of the UAV missions, is time-consuming relocations of ground control stations. As mentioned before, the ground control station is linked one-to-one to the drone. So if we have to switch off the ground control station and move to the new location, which is obvious in a linear object projects, then we lose one drone from the action. One drone cannot fly. So we pack everything to the car, we move to another place, and even if it is predefined place, it is troublesome to go to this new place sometimes, because you can imagine that four lines run across fields, meadows, forests, and it is not obvious that everywhere there is a convenient way to drive. It consumes a lot of time to move the staff to the new location and start again the mission. So concerning these issues, what are expected challenges for the system? The main technical challenge concentrates around distributed ground control station system. The system that would allow for controlling drones in many-to-many relationships. This means that one ground control station could control more than one drone in one time. And also one drone can switch the connection from one control station to another. This situation requires that the coordination of activities between control stations should exist, because they must exchange information and data about controlled drones and about the status of the entire project. If the drone reconnects from one control station to another, then this another control station should know everything about this drone, so the drone can continue the mission without any interruption. Another challenge is to allow for a coordination of route planning for all the drones participating in the project. To make the project flowing without any breaks, obstacles, this routes planning should be fluent without any breaks. And also the system should enable an ongoing reaction for different events or errors that can occur during the project. For example, should plan supplementary missions. For example, if one drone for any reason stops the flight, the system must plan supplementary missions so the next drone can start and continue the remaining part of the operation. Also, this could happen if the communication link, for example, decreases. Part of challenges are, let's say, challenges, but simply they are beyond our capabilities, beyond capabilities of the project, of the operators. But it is expected that if we enhance the efficiency of the system in a way that we described before, then it would be very helpful, efficient for operations which are performed in the beyond visual line of sight. This kind of operation is dedicated for large-scale projects, of course. But here today we face the, let's say, issues that there are, of course, formal procedures necessary to reserve the airspace, to inform everyone about our flights, to keep the local restrictions on the availability of the airspace. So today, this way of carrying out the project is much less flexible than we would expect. Nevertheless, all the issues and challenges raised before are relevant to BVLOS missions. And of course, economic issues, economic challenges, these actions, these challenges should end with the reduction of costs, because this is simply a business. So it is expected that the projects will be significantly shortened in time, and of course this would translate directly into financial aspects. We can reduce the cost of the project also by limiting the staff involvement. This would be gained by the automation of procedures. And of course, if we shorten the time of the project, the cost of equipment depreciation per kilometer or of linear project or per square kilometer of area project will decrease. And in such cases, at least some of costs of the insurance should be reduced. So according to these issues and challenges, what the solution is expected. So this is what was designed in the beginning for our use case. it is drafted on the picture above, and let's start with drones. There are here so-called edge devices. So the mission is performed with a group of drones. Each of the drone, in our case, is equipped with a camera which collects images of the power lines infrastructure. And on board of each drone, there is a module which controls the quality of images. And in ongoing mode, it checks whether the acquired image is correct or incorrect. Of course, this control can be done for different parameters. Can be simplified or not, but in fact, in the end, we know which image is correctly acquired or incorrectly. This would allow for ongoing verification of data quality and planning of eventual supplementary routes. And each drone carries out independently the part of the flying for the part of the project according to the part of the mission which is assigned by the control system here. Drones are connected with radio modem link to ground control station, and as you see, one control station can control more than one drone in time. The drone, after deployment and launching, automatically connects to the nearest ground control station, registers itself as an edge device in the system, and is ready for the mission. And continuously, it provides data about telemetry data about its position, speed, altitude of the copter, and they are transmitted directly to the ground control station, which controls the specific drone. Some words about ground control station. This is the main, let's say, part of the system. In the picture, we have 3 of them. The number of ground control stations in the system is open. We can have 1, we can have 3, we can have 10, 50, as many as it is necessary. And they are connected with drones, as I said before, with radio modem link and Mablink protocol. And they are also connected between themselves with the Wi-Fi connection. And with this Wi-Fi connection, they exchange information about the current mission status and information about flying drones. In this system, in a simple system, one operator is enough, and it uses a laptop with as a graphical user interface, and can supervise the mission, the project, and can give some controls to the system if it is necessary. What is the role of the ground control system in this in this situation? One of the basic things is that it controls the routes of the for the drones. In the beginning, it has to plan the master mission plan. So if we have the project which is 50 kilometers long, then the master route for this 50-kilometer length is designed, and then, depending on the current situation, depending on the capabilities of the drones, individual routes for the drones are designed and assigned to the drones. Taking into consideration also the different situations which can occur during the mission, like part of the data can be incorrect, so then supplementary mission can be again planned and assigned to the copters. Ground control station uploads flight plans to drones before it's taking off and transmits modification of the flight plan to the drone which is in the air. So keeps the constant supervising of the flying drone during the mission. This is what was said before, that maintains the connection with the drones and provide controls over more than one drone, receives telemetry data from the controlled drones, and maintains the exchange of data on the status of entire mission, its implementation, including the status of all drones being actually logged in. And is able, of course, to transfer the control of the drone from one control station to another if, for example, the radio link is limited. So this allows for the continuity of the mission. Okay, so let's describe now the system architecture. Here I give the floor to my colleague Jacek Piotrowski from our company, and he will describe the structure of the system.
Okay, so hello. We'll start with the big picture of the system. On the right side, we have drones, and with the fog computing terminology, we call them edge devices. We treat them just like remote controlled sensors that gather data. In the middle, we have a bunch of services that run inside the Rainbow cluster. And on the left side, we have an application with GUI that allows us to see what the drones are doing and where they are heading. This is an open source project called QGround Control. Okay, so let's discuss the particular services. The most important one is called Mission Guidance, and it's responsible for all the decision making in the system. Thanks to the Rainbow, we could just implement one service that makes all the decisions, because we can trust that there will be always exactly one instance of this service running somewhere in the Rainbow. And this is the service that receives from the operator of the master mission that needs to be then assigned in chunks to individual drones. And of course, the drones, while they are acquiring images, they send back information whether all the images were acquired correctly, if there are any errors or bad quality images. So this service can in real time check if all the data has been successfully collected. If not, it can plan reactive actions, send another drone to collect missing data. And since this service tracks the progress of the mission, it uses Redis cluster to preserve its state, so that if something happens to the node where this instance is running, the state will be preserved. We can restart the service, and it will continue its operations. The second service we call Radio Gateway. Its job is to route messages between MQTT topics and the drones over the radio links. And they were developed as an alternative to radio mesh, because the radio mesh requires expensive radio modems. We use simple devices that can talk to individual drones, and we implement all the mesh logic inside the software. The most important part is the handover algorithm, so that only one instance of radio gateway talks to the drone at the moment. So all the instances need to vote which one will be the active one. And when the drone moves away from one instance, it gets closer to another instance, the signal level changes, and these instances vote again to choose which one will be talking to the drone further. Next service is the ground control station gateway. It was just developed as a quick hack to allow to connect any ground control GUI software to the system. This way, we didn't have to modify this software. All it does is that it routes Mavlink messages between MQTT topics and TCP links. Of course, in the production version, we will have to simply implement MQTT support inside the ground control or any other ground control software. The central part of the system is the MQTT Broker that allows us to pass messages between services. We choose RabbitMQ, which is open source software, and it allows us to pass messages between services without paying attention to IP addresses, to the locations. Especially, we don't need to care which radio gateway handles the communication with given drone at the moment. We just send a message on a topic that is tied to a particular drone, and one of the radio gateways will pick it up and send it over the radio to the right drone. And there are two supplementary services. One is Consul, which is also open source project. It allows MQTT brokers to form a cluster. They need to find themselves inside the rainbow. And the second one is enumerator, which we developed as a way to assign ID numbers to radio gateways, because we need to know, they need to differentiate itself from other instances, but we don't want to configure them individually. We just can have any number of radio gateway instances. We just set the number of replicas in the rainbow, and they will get individual numbers, and we can proceed with the voting algorithm. Okay, so when we get back to the big picture, we can now see how the data flows through the system. And okay, so we have drones that stream data about their position, angles, velocity through the radio link. One of the radio gateways picks it up and posts it to the MQTT broker. MQTT broker sends it to mission guidance, and mission guidance tracks the state of the drone, checks whether it completed its mission or not, and the other way around, it can send commands to the drone to program it to give it a flight path so that it can collect data. At the same time, the ground control station gateway can listen to these messages sent by the drones, so that we can see on a map where the drones are located at the moment and where they are heading. Of course, when something happens, we can also give commands to the drones through the ground control station directly to the drone, bypassing the mission guidance. And these two services only take part in the system initialization, so they can just give the numbers, allow the MQTT broker to form the cluster. But the most important part is the mission guidance and the radio gateways, which are talking constantly through the MQTT. And now I would like to discuss a bit what are the benefits of choosing Crable as the basis of our system. And first of all, one of the main requirement is that we can deploy the system very quickly. So there is no setup. We just take a node, put it somewhere in the field, power it on, and it should start to work. And so the solution is to have a system that can configure itself, especially configure the network and make all the nodes discover themselves in the cluster. And the Rainbow provides a mesh networking layer out of the box. You just switch on the node and it will join the cluster automatically. And also the Rainbow will automatically deploy all the services to the right nodes. Also, the system must be secure, because a hijacked drone can injure people. You are also flying near critical infrastructure. Damaging power lines might be very dangerous, not only to people, but also to devices, and it's a big liability. So, since we are using Wi-Fi links, which are not very secure, as Wi-Fi has a long history of security problems, the Rainbow gives us a strong network traffic encryption out of the box. But what is more important is that also the Rainbow includes the attestation. So we can be sure that all the nodes that joined the cluster can be trusted. So we don't need to implement all the security on the level of services. It's already in the system. And the third element is that we want to pay attention to what the drones are doing. We don't want to care about the system during the mission. And so we would like to have a system that will tune itself and adapt to changing topology, to changing load. And we can achieve that with Rainbow through SLOs, service level objectives. So we can define rules that will adapt the system to its current state based on some metrics. And in our system, we have three such service level objectives defined. If we recap quickly, is that in our system, all nodes are interchangeable. There are no fixed roles of the nodes. They can be placed along the power line in any order. They can be switched on and off, and also they change positions in the along the power line. This means that the physical topology of the system changes constantly. And we have this main service, which is the brains of the system, and it needs to communicate with all of the drones. So ideally, it should be placed in the center node so that we can reduce the system latency, because if it's placed on the edge node, all the data needs to travel through all the nodes in the system. And it should be noted that we are using Wi-Fi links, but in a bit non-standard way, because it's not the kind of Wi-Fi connection that we have in an office or a home. Yes, our nodes are placed apart at larger distances, like a few hundred meters. So it requires that Wi-Fi routers switch to more robust modulation schemes that can withstand, provide communications for longer distances, but at the much limited bandwidth. So although we are using modern equipment, the Wi-Fi links have very limited bandwidth. And since the topology changes all the time, we cannot define the central node statically. Yes, so we need some mechanism that will do it automatically. And the solution is that we can have a service level objective with migration elasticity strategy that tells the orchestrator to place the mission guidance instance on a central node. In how we define the central node is the node with minimal network latency to other nodes. The other problem is that we want to deploy a radio gateway instance to all nodes with a radio modem, but there must be exactly one instance of radio gateway on a such node. And we don't want to set a predefined number of instances so that we can deploy any number of nodes in the system. So we would like the system to spread these instances to all available nodes, but this number should be determined automatically. And there is also a solution for this. We can write a custom SLO that will calculate the number of nodes and scale the deployment accordingly. Of course, we need to use also the labels and anti-affinity rules, so to ensure that there is exactly one instance of radio gateway on every node. And of course, this could be possibly done by setting the number of replicas to the maximum number of nodes that are available in the system. But this will mean that the orchestrator will be trying to deploy all these nodes all the time, and some of them will be in undeployable state, which is not an elegant solution. Also, as we already talked, we don't want to pay attention to what the system is doing. We want to pay attention to the drones and what is the data quality. We don't want to miss any spots, because this will cause a lot of costs. If we find a missing spot in the data collected, we have to go back to the field, deploy everything again, and redo the mission, at least the part of it. So the system should pay attention to itself automatically. And one of such problems is that if MQTT broker gets congested, all the communication will stop. So it would be good if the number of instances that form the MQTT broker is scaled accordingly to the load. If the load gets high, we increase the number of instances so that they can spread the work to multiple nodes. And this can be done with an SLO, with horizontal elasticity strategy, and we trigger the change of number of instances by tracking the CPU load of the instance where the broker is running. To sum it up, the Rainbow provides three elasticity strategies. The horizontal strategy allows us to change the number of replicas of given service. Vertical strategy allows us to change number of CPUs or amount of RAM. And we have migration strategy, so we can move the instances to different nodes. And these actions are triggered by expressions that we can define using some metric values. We can choose whether we want to calculate a maximum, minimum, average of given metric over a certain period of time. And we can also form expressions, arithmetic expressions with these metrics, and use this value as a trigger for the elasticity strategy. And of course, if something doesn't match these three strategies, there is a possibility to implement a custom service level objectives.
Okay, now let's switch to the description of use case, the scenarios, then results and conclusions. We've chosen three examples of the scenarios performed, and I will present them briefly here. This is the first scenario. The drone carries out the mission beyond the standard communication range. So as you remember and as you know, currently the drone, when flies, it flies to the first point of the mission, then continues the flight along the linear object. And in a moment when it is supposed that the ready link or visual line of sight will disappear, it stops the mission and returns to the starting point to land. But here in our use case, it continues flying, and during the time it switches the connection with from the first gun control station to another gun control station. So this allows it to continue the full mission and to perform the full mission up to the last waypoint and land near the next ground control station. So this is the first scenario. The second scenario is about several drones that carry out the mission, and there is a necessity to plan and assign a supplementary flight. So the situation is in the beginning, as in the first scenario, that the first drone flies and fulfills the full mission up to the end and lands, and another drone starts its mission in the point where the end of the mission of the first drone was planned and realized, and continue flying along linear object. But in some moment, due to any factor, it is forced to break the mission and land. So then the services which were described previously by Jacek, the mission guidance plans the next supplementary route for the third drone, which starts its route, the first waypoint of the route in the moment when the second drone finished broke its mission, and continue flying up to the end of the mission, and then returns and lands. And the third scenario, again, it from the beginning looks similar to the previous ones. The drone starts the mission from the first waypoint, continues, flies to the last waypoint of the mission. Also, the second drone fulfills the whole mission, but one of the drone has reported that some of photos were incorrect. So there is again necessity for the mission guidance service to plan a supplementary mission for the third drone, which is in blue here, to collect data from these two locations where there were incorrect photos. So these are three examples of scenarios for our use case. And they were tested for the first time in a virtual demonstrator, just to check if the system works well, if there is it is necessary to make some corrections and so on. And then the physical demonstrator was prepared and run. So here we will switch to the video showing how it was done in a virtual demonstrator. Let me switch the screen. Okay. And again, I give the floor to Jacek, who will comment the video.
Okay, so we see here the captured screen of the Q-ground control. Just as the operator sees it during the mission, the yellow line is the master mission. And we have 3 drones. One is located here and 2 others are here. And in a moment, the first drone will start its mission. They are set up in such a way that they cannot fly the whole mission in one go. So it will be assigned a part of this mission somewhere around here. The mission will be split, and the first drone will fly the first part, the second drone will fly the second part, the third drone will be used as a backup. So you can see that the drone is gaining altitude, and we now speed up the video 10 times because it would take a lot of time to them to travel. And at the same time, the second drone also became armed and received the mission, and we see the both drones are flying towards the simulated power line. And the second drone already started acquisition. The third one goes to the beginning and will also start acquiring images around this line. Okay, so now the first drone reaches the part where the simulated defects will be introduced. A bit of here and a bit of defects here, so we'll have to plan a supplementary mission. Now we have switched to third drone to see what it will do. As you see, the vehicle 1 reaches the point where its mission, its acquisition phase ends, and now the third drone should arm itself and start flying towards the first place where the defects were introduced. At the same time, the first and second drone are returning to the landing point. You can see that the drone is gaining altitude, and we should go around here and then here and back to the landing point. Of course, the drone number 1 and 2, when they land, they will be disarmed and then will be ready to either receive another mission, or they will have to be switched off to replace the battery, and then after they are turned on again, they can fly another mission. And so we have just this part that was defective was assigned to the third drone. In this way, we have the complete data.
Okay, let's switch again to the presentation. Yeah. So this was the example of virtual demonstrator, and now this is the stuff which was used for the physical demonstrator. This demonstration flights were performed about 50 kilometers from Warsaw in an open field. So here you can see this box here contains the ground control station computer based on Jetson. And here are two communication components. One, this is radio modem for communication with a drone or drones. And second, this is Wi-Fi router for communication between ground control stations. We used 3 ground control stations. One of them was assisted by the computer with the QGround control application just to supervise the mission. This is the drone which was used for our tests. This is Geo Hoverfly copter, designed specially for photogrammetric tasks. It is light. You see that below 2 kilo, took about 1.7 kilo, but very brave in the air. It can fly during the mission with the speed of 10 meters per second, and can stand with the wind condition up to 8 meters per second. These are limitations concerning the flight with acquiring images, because it can fly, of course, with much stronger wind, but we must pay attention that the images are of good quality. It is equipped with a small FLIR camera, RGB camera, and it can operate in a completely automatic mode. And on board there is a module which controls quality of images. As you see here, we used 3 of them to perform all the flights in scenarios, defined scenarios. And it was performed in the same terrain as it was shown on the map of the virtual demonstrator. Okay, so the scenarios, the missions were performed successfully, but to confirm that the system works in a expected, let's say, way with expected results, some of measurements were taken, so-called KPIs, key performance indicators. And here I present some of them and also the achieved results. So the KPI number 1 is a time to pass the control over the drone from one ground control station to another. So this relates to the moment when, for any reason, the drone has to switch the connection from one control station to another. And this break of the connection should be simply short, to assure that there is a continuity of the mission. So what was the expected value? It was 4 seconds, and during our tests we achieved 3 seconds. It is enough to keep the drone flying without any disturbances, without any breaks. This is also the time where eventual fail-safe procedure operates when it is run. So it is enough for us to make the drone flying without any break. The second KPI, this is the increase of productive flight distance per drone. So this is obviously what is expected, that if we use the capability of the drone to fly longer distance without necessity to return to the starting point, we'll use this capability to fly over the productive part of the mission. So the expected was 50%. We achieved 100%. This is for the first look very spectacular, but I remind that this is in respect to the productive flight distance, not the total flight distance, but productive flight distance. And this is really, of course, a good result. As it is mentioned here, the result of the demonstrator was achieved by maximizing possibilities given by the drone system. Also the circumstances which were on the testing site. Then the KPI number 3, this is the reduction of data acquisition time per kilometer of power line. And this relates to the not single mission, but to the overall project. So if data are acquired by a group of drones, then this is the, I would say, average reduction time of data acquisition for the whole project, not for the single drone. We expected 50%, and we achieved a little over 60%, but it's still a better result than expected. And the last KPIs which is presented here, this is the efficiency of battery usage for a productive phase of the drone flight. So this is about how the energy of the battery is used in a more efficient way. So expected value was 55%, and again, let's say spectacular result, 167%, but still I am reminded this is this relates to the productive phase of the flight, not to the total mission, not to the total project, but the productive flight of the distance of the single drone. So the explanation or justification to this result is the same as to the KPI number 2. Okay, so as a summary of the project, it was successful. It was the test, the use case was successful, and it was very interesting for us to design and to perform such a use case in the project. In this moment, I can say that it was a pleasure to take part in this project. Thank you for inviting us for the Rainbow project and for all the help from the partners that were given to us during our participation in the project and the work with our use case. The project is not finished yet, of course, but it is a good time to give thanks to all the partners. So, as you saw, we prepared, designed and prepared the demonstrator, the virtual and the physical one. And we measured the results, and all of the results were better than we expected them to be. But this was a test on a small scale, I would say. And we paid a special attention that our test case will be conducted well, that according to the assumptions, and we try to keep all the use case parameters as strictly as possible. So the let's say remark here can be given that if we go to the commercial project, then I would expect that these missions, the project will be designed much more conservatively. This means that much greater safety margin would be applied to all the missions, and in this way the results could be less spectacular. These KPIs measurements would be much less spectacular than we achieved in this project, so would have been correspondingly lower. But still, we are sure that the results would be much better than the project carried out without the support of the rainbow system. So thank you very much for your attention. This is the end of our presentation, but not the end of the webinar. And I give the floor to Christina. We can have some time for the discussion.
Yeah.
Thank you.
Thank you both for your very detailed presentation, and also for the videos and the use cases that helped to understand the challenges that Rainbow addressed within your use case. I would like to address to all the participants if they have any questions or comments that they want to put forward. Hopefully they are still following the discussion, but either you explained everything really well, or they are now thinking of questions to pose. I would like to discuss a little bit more what should be the next steps for this use case, being towards also commercial exploitation, or how it can be extended or further tested. Do you have in mind detailed a detailed advanced scenario for the future, let's say?
This is a good question. Maybe not detailed. This is maybe too early for us, because the use case, as you know, was finished not so far ago, and it was still much work behind it. But we learned a lot about the capabilities of the system like Rainbow, and we learned a lot, gained a lot of knowledge, and we have some let's say projects which are running in parallel to Rainbow, where we think it can be the results can be used and implemented. One project relates to to the power lines inspection. So this is exactly the team which is in our use case. But in this case, I'm talking about the manned system, not unmanned, but manned system. Which is and in this project we designed and developed the fully automatic model which gathers data about power lines infrastructure. There is a two inspection cameras with a very high resolution, small camera looking vertically down to gather orthophoto images for orthophoto, laser scanner to collect point cloud, and also camera used for the automatic detection of power poles. The detection camera constantly searches for the power poles, and if the pole is detected, then it directs all the head with cameras to the power pole, and there is a continuous collection of all the data. The system works completely in an automatic way, but it is mounted under the small manned helicopter piloted by one pilot. There is no more on board, and we expect that the knowledge and experience from Rainbow we can introduce into that project. It is, as I said, a little bit too early for a concrete solution, but as I said, this is the project which is run in parallel. So in the near future, we expect that we can use all the experience in this other project. And the second our idea relates to let's say not civilian project, so I cannot tell too much about it, but we also think to use the idea of the solutions which were seeded by Rainbow project, but this is, let's say, further future than in this first case. But we have in mind that the Rainbow and solutions which were developed here would be really helpful. Thank you.
Yeah, indeed, the scenario with manned drones, it's very interesting. It sounds very interesting, at least. Another question that I have, unless we have someone else to pose a question, but another question is that do you prefer some functionalities of Rainbow more, or did you miss a functionality or a feature with regards to your use case that could be helpful, but it wasn't part of the Rainbow platform? As a suggestion or a recommendation for the Rainbow platform to be improved, let's say.
At this moment, we don't have any suggestions like this for the use case. Everything worked really well. We appreciate very much the possibility to switch the connection from drone between the ground control stations, and this helps a lot in the improvement of the overall mission, overall project. So this is the main let's say advantage in our use case. At this moment, would not suggest anything more. Maybe this too early, or we will probably have suggestions like this when we we'll start to think about implementation of Rainbow solutions in other projects. This would be, I think, a good time for it.
Okay, thank you, Vinek. Are there any further questions from other participants? Okay, I understand that no, so we can wrap up the webinar at this point. I would like to thank you once more for the very detailed presentation that you prepared and the videos that accompanied the presentations were really helpful, and we took an idea of how Rainbow facilitated your case and the work that you performed as well. So thank you once again, and thanks to all participants that joined. I will stop the recording now, and we can close the meeting.